I am going to talk about the dynamics of quantum measurement. What really happens when we say we have measured a quantum state? This is a question that has been around since the birth of quantum mechanics, and the reason we have been able to say something more on these old historical questions is because of technological development. So there are both theoretical parts and experimental parts to this talk, and our contribution is in these two papers. First is theory, the second is experiment. So let me start with the description of quantum state in terms of a density matrix. It is the generalization of probability distribution in the classical physics, and this describes the complete information that is contained in a quantum state. It has real diagonal elements, which are the classical probabilities of observing various eigenstates, and the off-diagonal elements, also often called coherencies. They describe correlations between the eigenstates. For pure states, rho square is equal to rho and determinant rho is equal to 0. And these relations have important consequences that you try to construct any non-trivial function out of the density matrix, and it becomes a linear, any function rho becomes a linear combination of rho and I. Any power series will come down to just a linear result because of this identity rho square equal to rho, and the determinant vanishes. So the only thing you can do after that is take a trace of this function with any observable, and these are the expectation values we have in quantum mechanics. And Wigner functions, which we heard about in the morning, is actually a particular representation of the density matrix in the phase space, but it illustrates the points which appear when dealing with density matrix, that you can convert the values encountered to all reals. You can even normalize them to unity, but sometimes you have to face the fact that some entries are negative, and that becomes the quantum signature, which I will have to come back later in my talk. Okay, what is the method used to study the density matrix? We are going to look at the framework of weak measurement, and I am only going to use it in one particular sense, that the coupling between the system and the apparatus is small, or in other words, information is extracted from the system at a very slow rate. Nothing more than that. No weak values in particular. What this does is it stretches out the time scale over which the quantum state collapses to one of the eigenstate, and we can use this extended time scale to see whatever is happening in the intermediate steps. And that allows us to go beyond the usual framework of quantum mechanics and see the details of the measurement dynamics. What we need as a consistency check is that if we perform such weak measurement experiment many times, create an ensemble, then we should get back the Born rule in terms of the probability distribution of which eigenstate is observed how many times. But what more is buried in this description, that we can look at individual runs of the experiment, which will be labeled as quantum trajectories, and whose stochastic dynamics specifies which particular eigenstate will occur in which particular experimental run. This is the part which goes beyond the textbook quantum mechanics. And we have to have strong constraints because we don't want to violate whatever we know already about quantum mechanics. The eigenstates are fixed points of the evolution, and that requires the evolution dynamics to be nonlinear, otherwise it will never stop. It will just keep on going round and round in unitary evolution. And the probabilities of observation of various events should not conflict with the Born rule, and the only way we can achieve it is that make Born rule as a constant of evolution. It doesn't change as a function of time. So you can stop at any intermediate point and check it, and it still is completely all right. It also avoids any conflict with special relativity, where there is no concept of simultaneity left, and measurements cannot be ordered in different ways in time. Okay. And this seems to be a tall order, but a solution which obeys all these ideas was written down way back in 1994 by Nicolas Disson. What are the important features of the solutions? The theoretical derivations I can give, but there is not enough time for doing all that. I will only give a summary. So the process is actually a stochastic process. There is a certain amount of driven evolution which takes the initial state to an eigenstate, and on top of that there are fluctuation, and it turns out that when the fluctuation and the driving term are related in a particular way, then we will get the Born rule. If you don't have the relation between the fluctuation and the dissipation rate, Born rule will be violated. This is an unusual connection. The other thing which happens is the dynamics is completely controlled by the interaction between system and the apparatus, and we can forget about the rest of the world. Or in other words, the rest of the world can influence the measurement dynamics only by a process which will go through the apparatus, nothing directly. This is also something which is very peculiar, and I will show how that arises. And the picture which we'll have at the end is the measurement will be an effective process of something which is more fundamental and deep. What this more fundamental thing is, we don't really know, but the experimental result will give us clues about in which direction we should search for. And the geometrical picture is something like this. You start at an initial state. It's a zigzag process which will end up either at one eigenstate or the other. The classical analogy on statistical mechanics is this is some kind of Brownian motion. Okay. It's not a monotonic evolution. It will go all over the place, but somehow it will find its endpoint. Okay, so what is the dynamical equation governing this process? I will just write down the answer. It has this particular structure where rho is a density matrix. Pi's are all the eigenstates of the measurement, also called the pointer basis. There is a coupling which dictates how fast we are going to evolve in this particular direction. And there are various weights which specify how often I will go to which particular eigenstate. I have normalized it because the g is a global constant. I can make this sum over all the weights equal to 1. So this is the structure of the equation. It turns out that this term which is in the square brackets, it gives a geodesic evolution which takes the rho, the initial state, to the pi, which is the pointer states, along the shortest path in the Hilbert space. And the weights are then something else which will specified next. But this structure is very interesting. In particular, it preserves rho square equal to rho. That means if you start with a pure state, it will always remain a pure state. Trace is preserved, and so it creates a dynamics which is very different than the von Neumann prescription. The state is never entangled with either the apparatus or the rest of the world. It is always pure. But you have an interaction. All the pointer states are fixed points of the evolution, so if you go there, the derivative becomes 0. You stop. And on top of that, the diagonal elements of this equation, if you write down, they will completely tell you how the off-diagonal elements are going to evolve. So even though the equation is written in the matrix notation, it has only n minus 1 independent degrees of freedom, which are the various probabilities. The trace rho equal to 1 removes one total normalization. And this evolution is therefore completely decoupled from the decoherence process, which tells you how the off-diagonal elements will evolve. This is the evolution of only the diagonal elements. Okay, one more thing I can point out to this particular audience, that this operator which is written here, it's actually the Lindblad operator, but it is a Lindblad operator acting on the apparatus, and the interaction is coming from the density matrix. So it's the whole thing which is flipped. Somehow the system is decohering the apparatus, and the sign of this term is such that there is an overall negative sign compared to the Lindblad operator. So it is the system decoheres the apparatus, and this is the back action on what happens to the system in the process. That is the mathematical structure of this operator. To get the bound rule, I have to choose these weights about how often I go to which eigenstate in a clever manner. If I just make a simple naive choice that this weight is just the bound rule condition, the trace of rho pi, then the equation doesn't give me the correct quantum description. It just goes to the nearest fixed point. It's a deterministic evolution, and that is not we want. So we have to add a noise to these particular weights, and by adding the noise, things wander around in the Hilbert space and just don't go to the nearest fixed point. How much is the noise, and what is the nature of the noise? It is not a universal criterion at this point. It depends on the choice of the apparatus and the interaction. But I can say that if I put too much noise, then all fixed points become equally reachable. It's a democratic thing. So too little noise, I go to the closest point. Too much noise, I go everywhere with equal probability, and the correct answer is somewhere in between. That right amount of noise, I will get the bound rule, which will say I will reach this fixed point with this probability. Each noise history actually can be a label for an individual experimental run. In some sense, one of the many possibilities in the ensemble. And when I add it up, I should get back the usual quantum description given by the Lindblad master equation. The individual trajectories are behaving non-linearly, but the ensemble average description becomes linear. That is also a peculiar feature. And there is a lot of freedom involved. In particular, measurement time is just defined in terms of a parameter. You can redefine the parameter and adjust what you will want to label as a collapse time scale by changing the value of the coupling or even making the coupling time dependent, etc. So we tested this equation in the setting of a single qubit. And first I will say what the dynamics for the single qubit is. That differential equation reduces to just one parameter equation, which looks like this. W0 and W1 are the probabilities of the two eigenstates 0 and 1, not probabilities, the weights for the two eigenstates, and the off-diagonal element is completely determined by the diagonal elements. It's a single variable equation, and turns out that even though it is a nonlinear and complicated looking equation, it can be exactly solved. So that is a good point. And you can solve it for many different situations. I'm going to use the situation where the equation is similar to what is studied heavily in statistical mechanics in the framework of Langevin dynamics, where the noise is taken as a white noise, zero mean and delta function correlation. And so the weights are what is predicted by the bound rule, rho 0, 0 and rho 1, 1. plus this noise, which is a fluctuating term. And that is what goes inside this equation, and then all the predictions follow. It's a stochastic process on the interval 0 to 1. The boundaries are perfectly absorbing. If you go to the boundaries, the evolution stops, and in between there is a lot of zigzag, and this is a kind of scenario which you find when you start from somewhere over here, and either you land up on one side or the other. The important point to keep in mind is the evolution is not monotonic. That is very different than the description of either decoherence or collapse. You can go close to over here, and there's still some probability that you will flip over and go to the other side. Okay, so to find the solution, it is convenient to write down the differential equation into what is known as a Ito form, which is described in statistical mechanics as a random walk. There is an increment d rho, and it is specified in terms of a drift term which is proportional to dt, and a Wiener noise, which is dw. This dw square proportional to dt is the random walk signature, and the average value of dw is 0. The condition for Born rule turns out to be the situation where this random walk has no drift, the coefficient of dt equal to 0. And that amounts to putting this condition g as equal to 1, and then the increment vanishes, which means that the Born rule becomes a constant of evolution. The expectation value of rho does not change as a function of time. But it's also peculiar that you can calculate not just the first moment, but the second moment of the same term. And it turns out that the second moment is proportional to the geodesic term, which is the drift term in this particular form, without any dependence on either the coupling or the time. So it is a completely dimensionless relation. It relates the first moment and the second moment, reminds us about the fluctuation dissipation connection in the Brownian motion in statistical mechanics, and what other implications this relation has, I don't know. But it has a very powerful implication that the environment can influence the measurement process only via the apparatus. The reason being that the drift term is produced by the apparatus. It's telling you that you should go to this particular eigenstate. And the noise, which is all fluctuations put together, cannot equal this thing unless the noise is also limited to whatever is producing the drift. If there is an extra source of noise, this proportionality will be lost. Okay, the equation is a Langevin type. The way these things are usually solved are converted to a Fokker-Planck equation, which will give you a distribution for the variables as a function of time, and you can solve it. The solution has a nice structure. When the interval 0 to 1 is mapped to a whole real line, then the solution becomes a sum of two Gaussians, which is quite nice. Gaussian is a diffusion process. A generic solution of a diffusion process is a Gaussian. But here, the solution is such that the initial state separates into two Gaussians, and the two Gaussians just monotonically go towards two eigenstates. There is no interference between the two Gaussians at all. The area under each Gaussian is a constant of evolution, independent of time. So they almost behave like solitons. These are all very peculiar feature of this equation. And on top of that, there is only one parameter, which is this coupling G in this whole description, and which makes it experimentally testable that I have a theoretical prediction, one parameter evolution, check it against what I can do in terms of experiment, and the parameter is, here I have been writing G times T, but more generally, the coupling can be time dependent, and then the only parameter is integral g dt. That's it. So now let me go to the experiment. I will not go into the detail, but the experiment was performed on what are called transmon qubits. They are superconducting devices based on Josephson junctions, and they behave as nonlinear oscillators. They are popular these days because they have a long decoherence time, much larger compared to the individual experimental operations, at least by a factor of 100 or so. So you can do many things before the system gets destroyed by the environment, and there are a lot of technicalities of how they are manipulated. Particularly, the whole experiment takes place through a microwave resonator, and high accuracy measurement are made by extracting only one quadrature of the signal and throwing out the other quadrature. Okay, so this is always done, and it has to be done with a millikelvin temperature and a very phase sensitive amplifier to keep all the errors under control. And what we did was created a qubit polarized in the xz plane and measured it in the z basis. So the starting state is known, and we are monitoring how it evolves, and we can evaluate it as a function of time until it reaches one of the eigenstates. There is a well-known formulation of how that can be done. Provided you know the initial state, you can measure the current, which is the signal coming from Wick measurement. It is measured over a short time interval, and the value of this current will tell you how the ratio of rho 0 0 to rho 1 1 changes to next interval. In practice, we have to take into account an extra feature which is not there in the ideal case, is that excited state decays at a certain rate. This time is much larger than delta t, but still it has a significant effect, and we can include it by doing an alternative evolution between measurement and this exponential decay, and that allows us to construct trajectories that can be collected in a whole data set, and then you can measure its distribution, measure its correlation, all features like that. And what we did was we collected a whole data set of trajectories and fitted it to the answer obtained from the solution to the Fokker-Planck equation, which had a one parameter result in terms of this integrated coupling. Well, there is a second parameter because we had to take this relaxation time from an independent experimental measurement. And here is a sample of the type of results we got. The initial state starts with a delta function, and you can measure the distribution of the trajectories at various amount of time. This is 1 microsecond, 5 microsecond, 10, 15, 20, 25 microsecond. What happens is the distribution spreads, and it divides into two peaks. One of them goes to one eigenstate and another goes to another eigenstate. There is an asymmetry which is visible over here, and that is because the excited state keeps on decaying into the ground state. So that has to be included in the bias. But the important point is that the red error, not error, the bars over here represent the experimental data. Divided into 100 bins in this interval 0 to 1. And the blue curve is a theoretical fit with a single parameter. And there is a very good agreement. There can be some mismatches like here, but the goodness of the fit is measured by this value of chi-square. There are 100 points, only one parameter. So if you get chi-square of the order of a few hundred, it is actually a good fit. So this is the data, and it fits the theory. This is just an illustration. We could do the experiment with very many different choices of parameters, and some of it is illustrated over here. The 3 curves over here represent different starting state, and they all fall on top of each other, means that the coupling which is there between the system and the apparatus is independent of the starting state. And if you change the value of the coupling, the whole parameters shift, but they all shift together. So this is one value of the coupling, this set of points are the other values of the coupling, and we can change this coupling, which determines the time scale of collapse, by just adjusting control parameters of the resonator without changing any of the other things like position or size or the mass or the apparatus. Nothing of that changes. It's only the tuning resonator parameters which allows you to change the coupling. So the collapse time scale depends only on that and none of the other features as well. So this is a answer, and well, some caveats which we have to take care of. There are systematic errors because experiments have their own what you call imperfections, and which are not in the theory, and you have to take care of it. For example, there are extra photons in the cavity which disturb the signal. What we have is actually a transmon and not a two-level system, so some contamination comes from other excited states which mix with it, etc. But we have to estimate all the corrections for that, and those are included in the error bars. Okay, so that leads us to the question that if this theory agrees so well with the experiment, how well we can understand the various ingredients of the theory. So that amounts to ask the question, what is the origin of the noise which was stuck in the theory just by hand? We put in, because it was needed to get the description right. One thing I said that it can be viewed as a back action of the decoherence of the apparatus, but what more can we say about it? One thing which is obvious is that whatever we have seen has improved our understanding of measurement, because what it has done is it has replaced the Bond rule by a new equation and a noise which is independent of the system. So the noise is completely dictated by the apparatus. It doesn't depend on what you are measuring, how you are measuring it at all. And you have an equation which governs the dynamics, which is well specified. So that is progress, because you replace one postulate by something which is independent of the state. You have a well-defined equation, and you have a system-independent noise in the analysis. The noise depends on the apparatus, and I can only guess how it can arise, that somehow the amplification process produces a certain amount of noise in the apparatus. The most quoted example is spontaneous versus stimulated emission in any amplification process. And there is an inherent uncertainty which is buried inside there. That can be the source of the noise. And if we understand this noise, probably it has to do with how clearly we can understand coherent states. We can probably figure out some details, but it definitely requires making a model of the apparatus. Without that, we cannot understand the origin of the noise. But what we can say something about is the nature of the noise itself. Is the noise classical or quantum? Is there any signature in the observations which tells you that this is a quantum process and not a classical process? So that amounts to, can we say something about the statistical feature of the theory which is different than what is there in Brownian motion? Brownian motion is the conventional classical description of a stochastic process. This is also a stochastic process, but does it have anything which is different than what goes inside Brownian motion? And the answer is yes, because I introduced these weights in the analysis, or the weights, how often I go to which particular trajectories at this particular parameters. So the weights were a combination of the Born rule, that particular density matrix element plus the noise. But when I do that, the weights are no longer bounded between -1 and 1. The Born rule term is bounded between 0 and 1, but this combination is not. So it is going outside this interval. So rho 0 and rho 11 you can call them probabilities, but W0 and W1 are not probabilities. And they are going inside the equation. What do they do is actually possible to track in the signal that we have seen, that we have constructed this trajectory which tells you how this rho 0 and rho 11 change. The theoretical description says that it changes according to these weights and the coupling G. The experimental description says that it changes equal to depending on the value of the current which we see in the apparatus. And what we can say that when these weights go outside this interval, this current signal becomes either larger than rho 0, 0 or smaller than minus rho 1, 1. We can directly see it in the trajectories that we observe. So we have the values of this thing as a function of time, and we can spot at what point they are going outside these bounds from the experimental data. And then the question is, can we quantify it? These are these excursions outside this interval, and they are responsible for non-trivial features in quantum dynamics, which is different than the classical dynamics. And they are the signatures that we are using genuinely different things than classical weights. And this experimental data can be converted into certain correlations which will quantify it in terms of certain inequalities. First, I was trying to see whether I will have to do a 2-qubit measurement on a singlet state to see peculiar correlations, but I have not been able to solve the evolution equation analytically for this particular state. But it turns out that it may not be really necessary. Just the temporal correlation again of this signal, as in the case of Leggett-Gugg inequalities, will probably tell you which are the points the excursions are outside this interval, and then they will be quantified as a violation of certain stochastic processes which cannot occur in classical physics, but they occur in this quantum evolution. And that will be really a non-trivial result, and which will be very interesting to derive. I have not found the answer yet, but I am working on it. Thank you very much.
Thank you, Apporva. There exists, as you know, a whole host of measurement models, beginning with von Neumann, and more recently, many models constructed by Ozawa. Does your Brunel equations, which you at one point say that the state does not get entangled with the apparatus?
Well, I have observed the experimental distribution, and you can try fitting it to whatever the other models can predict. And some simple-minded things I have tried, and they certainly predict very different things than what this what is known as a quantum diffusion model, that is a label for this particular equation. What it predicts is very different than what the von Neumann interaction will predict or what the short noise model will predict. But only for certain specific situations we can compare. There is no global statement that it's all other models are ruled out.
Yeah, the von Neumann, of course, is important because it's the earliest. But the constructions by Ozawa go over a variety of constructions. It's not just one construction, this set of constructions. And it is the kind of thing which can be used as a workhorse to see how much selective
I have not compared it with that, so,
Okay.
well, so it's something that can be done. Yeah.
Any other question or comment?
Just wanted to comment on the last point that you made. That is, what is the quantum or classical nature of this? So I just want to say that I learned that in classical stochastic dynamics, statisticians have done that is the analysis of Brownian motion. And there is Hudson-Partsarthi theory which extends it to quantum operator valued processes. So from the operator valued processes, it can be seen that depending on the kind of measurement, you will get the jump-like trajectories or the diffusion-like trajectories depending on the measurements. So this is something to do with, from classical stochastic dynamics, when you try to extend it to quantum case, you have to have non-commutative operator algebra. So it is, these things are intrinsically quantum in that sense. So, but then details of the process, I don't know that what you are saying. But it is something like a statistical generalization from probability theory to non-commutative operator valued processes is what I have learned. That's a comment that I wanted to make.
No, that is certainly valid. What I was trying to point out is from the experimental observables themselves, you can construct certain quantities. And the job is to find such quantities where you can put bounds on them according to the classical theory, and the quantum theory will go outside those bounds. Similar to what John Bell did, saying that, okay, everything which is local hidden variable, we can only produce this. So something similar should be possible, that's what I believe, but I have not been able to put my finger on that this is a particular variable which I should look at.
Just one quick question, if any.
So if you add stochastic term to state vector, the evolution of state vector, then if it is coupled with the special wave function as you wrote Gaussian wave function, then it then continuity equation for that wave function becomes is not valid, right? If there is a stochastic term in wave function, then if you write the continuity equation, it won't hold. Will it?
The trajectories are still continuous. They are not going to violate the norm or the trace row equal to one condition at any stage. They are not differentiable. That is a property of the white noise kind of solution, that yes, you have continuity but not differentiability.
Okay, thank you.
Just on the question of classicality again. So, I mean, I guess one reason why I don't see how you would find the Bell type analog that you're looking for. I mean, because on this, at least on this page, I mean, in general, of course, you have preservation of pure states, etc. But I mean, everything on this page refers to just like the diagonal elements, rho 0, 0 and rho 1, 1. So it seems to me that if you just had a completely decohered qubit and you were measuring that all of the same maths would still apply for talking about the populations, and that, of course, can be understood classically. So I guess that's, yeah, just maybe a reason maybe not to be too optimistic about finding some proof that it's non-classical.
Yeah, I don't know what the exact answer is. I'm still searching for it, but this is intuition of what may happen, and I'm just trying this particular direction. That's all I can say.